Okay, so let's do that. Let's look at linear regression again. Let's actually look at the example from last Thursday in Mathematica to start with. Find my Mathematica here. The zoom thing's in the way. Here we go. So remember, it was about connector length and pitch of computer connectors. Connector length, they mixed up the units, was like in inches and pitch was in millimeters. This was X, the X data, this was Y data. If you're going to do this kind of thing in Mathematica with regression, not that you have to do it this way, but you can enter the X and Y data separately into lists with curly braces like this. And then if you want to merge these data into one data set of a bunch of points, well, if you do this, this doesn't quite work because it groups the points together in the wrong way. Here it just puts the X data all together like that and the Y data all together like this. As a matrix, it's representing it as a 2 by something matrix. I think it's 12 data points here, 2 by 12 matrix. So what you want to do instead is you want to take what's called the transpose of that matrix. Now, as a list in Mathematica, it's a list of points. You could think of each of these things as being a point, an XY point. And if you want to see what this is as a matrix, it is now a 12 by 2 matrix instead of a 2 by 12 matrix. It just switched. The first row of the first matrix became the first column, and the second row became the second column. And this is the way you want to deal with it as points. And so now I'll just call this data. And the way to see what the fit is for the data as a linear regression line is to use a command called fit. Then you type the variable name for the data, then put inside curly braces a 1 and an X representing the fact that we're trying to fit these data with a linear function of X. That's the reason why you do it this way. And then put an extra comma X to emphasize the variables X. And there's your equation for your regression line right there. Slope of about 25.4 and y-intercept of about -0.003. And this does match what we got with the Excel last time. Slope of about 25.4, intercept of about -0.003. Okay, so that's how to do it in Mathematica. It's actually quicker than what I showed you with the spreadsheet last time, though there is a quicker way to do it on spreadsheets that I'm going to show you today. That is, well, it's hard to do it on Excel on a Mac. You can do it on Excel on a PC fairly easy. I don't have a PC, I've got a Mac, so I'm going to do it, instead of doing it in Excel, I'm going to do it in Google Sheets, Google Spreadsheets. I'll show you how to do it. But before we do that, let me emphasize something else. Let's emphasize the meaning of SSE. Remember that? SSE is sum of squares of errors. This thing as a function of B0 and B1, the unknown intercept and slope of the regression line. So I'm going to essentially plug this into Mathematica for the data that I have and treat it as a function of B0 and B1 and try to optimize it, try to maximize it, or excuse me, minimize it. We're trying to minimize the SSE. So I'm going to go back to Mathematica here. Let's see if I can get both these things on the screen at the same time so you can see them both. So here's the Mathematica, and then we'll go back and show you the book here as well. SSE formula right there. And now I'm going to essentially try to type that into Mathematica. How? Well, I could go SSE. It's a function of B0 and B1, the unknown intercept and the unknown slope that I'd like to find. It's the summation. Go ahead and press the summation button. I goes from 1 to 12 is the data, the length of the number of data points here. N is 12. How do I type what you see in the parentheses there in the book? yi minus b0 minus b1 xi. Well, the y's are the the pitches, pitch y, and the x's are the con length x, pitch y. How do I get the ith value? Here's the way to do it in Mathematica, like that, with double square brackets and put an I in there. That's going to give you the ith value of the list y, pitch that I'm calling pitch y. Minus B0 is unknown, just type it as a B0. B1 is unknown, type it as a B1. And then xi, that's the con length x, double square brackets and an I. Excuse me. So this is the function SSE. If I do this, Mathematica actually expands it out as a summation without a summation sign. That's the function we're trying to minimize. We're trying to find the values of B0 and B1 that minimize that. That's why this is called least squares linear regression, because that's a sum of squares and we're trying to minimize it, least squares. Why is it called regression? I'll come to that later. Where's the word regression come from? It should have a connotation that sounds like, it seems kind of negative. You're regressing. And actually, it is kind of negative in the historical, when it historically originated. It does bring up images of regressing to the mean, if you've ever heard of that phrase before. That is actually analogous to the idea of a sophomore slump in sports, where like whoever was rookie of the year the previous year usually doesn't do as well the next year. And it's not necessarily because all the other players are aiming after that person, but that might be part of it. This is a function of two variables. Multivariable calculus. I could plot it. How? Not an ordinary plot, but a plot 3D. B0 ended up being close to 0, so I'll let B0 vary between -1 and 1, say. And what did B1 end up being close to? I forgot already. 25, yeah, okay. I'll let B1 go from 20 to 30. What are we going to see here? It's a function of two variables, multivariable calculus. The graph is a surface above a horizontal plane. Usually you label the horizontal plane with axes x and y and the vertical axis with z. But here it would make more sense to label the horizontal axes with B0 and B1 and the vertical axis with whatever you want, I guess. And it should look like it's got a minimum. That's reasonable, at least. If you want to, it might look like it's got a lot of minimums. Might look like it's minimized all along this bottom part here, this trough. It might be more clear if we make the plot range a bit smaller in the vertical direction, like instead of 0 to 20, like you see here, maybe 0 to 2 or something. That's looking a little bit more clear that there might be a minimum value somewhere close to 0. SSE, its minimum value is close to 0, as the spreadsheet can confirm, actually. We did this last week. We saw SSE, its minimum value is very close to 0, 0.0005. That doesn't always happen. In fact, you might say it usually does not happen, and it's that close to 0. If we zoom in even closer to what we know the answer is, it should be more pronounced, perhaps. We know the true answer for B0 is -0.003 or something. So if I go -0.1 to +0.05, and we know B1 is close to 25.4. So if I go 25 to 26, it might become a bit more clear, maybe if I make this smaller, that there truly is a minimum at one point. Maybe I should try to go. Let's see. No, okay. Yeah, okay, that's becoming more clear. There's the lowest point on this graph. It is minimized somewhere. if I differentiate it, if I find partial derivatives of this function with respect to b0 and b1, yikes. It looks kind of crazy, but actually if you expand it, it simplifies quite nicely. That's the partial derivative with respect to b0, and the partial derivative with respect to b1 simplifies to this. Those are effectively the normal equations, not in the standard form. Effectively, they're equivalent to these things at least. And it's the solution when you set those equal to 0 and solve for b0 and b1 that's going to give you your critical point that is going to be a minimum. Even if you haven't had multi, just like Calc 1, find the derivative, set it equal to 0, solve for the critical points. You do the same thing in multi, except you've got two derivatives. You've got two partial derivatives to set both equal to 0 and solve for both b0 and b1. So if I set these equal to 0 and solve for b0 and b1, ignore the apostrophes. That's just Mathematica's way of saying there's more decimal places it's keeping track of internally. We should get our old friends, the negative 0.003 or something, and the positive 25.4. Oops, we didn't. How about that? Maybe because we've got too many decimal places. I'm not sure what's going on here. That was surprising to me. Is it possibly because these are so sensitive on the decimal places? Well, there we go. Okay, that did affect it, and those are the right answers. So usually that doesn't happen. So I don't know why it happened in that case, but getting rid of those extra decimal places and with the apostrophe helped, and there are our answers again. Is it really a minimum? Well, it certainly looks like it. There is a multivariable calculus version of the second derivative test that can confirm analytically that it is a minimum. It is. We won't bother doing that. And yeah, if I find SSE of negative 0.003164, comma 25.4428, I should get that very small positive number that we saw in the spreadsheet, 0.0005. Any other values of B0 and B1, any other line that you try to use to fit the data is going to produce a value of SSE that's bigger. It's this particular intercept and this particular slope, approximately, that give us a smallest possible value of SSE, and that's why we quote unquote scientifically say this is the best line to use, the line of best fit. Is this the only possible method somebody could use to find a line of best fit? And could other methods produce different answers? Yeah, you actually could use other methods, and they actually could produce different answers. Instead of minimizing a sum of squares of errors here, you could try to minimize maybe a sum of absolute values of those differences instead of squaring them. That would be another approach. And it probably would produce a different answer, actually, though that it might not be too much different. However, absolute values, you know, are kind of a pain to deal with. And differentiating them is even more unpleasant. So that's why we prefer to sum the squares instead, is because it's easier to deal with mathematically. But that would be an alternative approach. Take the absolute values of those differences instead of squaring them. Okay, so just some big picture ideas there. I was thinking of going through this derivation by hand. It's not too hard. You can do this fairly easy, rearrange, get these normal equations, it's fine. I don't think I'll take the time to do that in class. What do we want to do for the rest of the day today? We want to do some basics of inference in this context. Before we do that, though, I should show you how to use a spreadsheet, either an Excel file if you've got a PC, or Google Sheets if you have a Mac, which is what I have again. Let's see, where do I have it here? There it is. To set up your Excel on a PC or Google Sheets on a Mac to do regression analysis, there's a number of things you can do. What I'm used to doing, though it may not be best, is to use a certain add-on called XLMiner Analysis Toolpak, which is not necessarily in your spreadsheet by default. And I know it's not on Google Sheets. I've got it here on my Google Sheets account because I've added it. It's an add-on. If you don't have it, and you should write this down, you can load it. We can do a search for XLMiner. There it is. I've installed it already. So I'm in Google Sheets. I went to the add-ons menu. XLMiner Analysis Toolpak is what I use. It's what I'm used to. I was noticing just today that XLMiner Analysis Toolpak it's got a lot of downloads, but it doesn't get a very good ratings compared to this other one that I just saw here, Logic Sheet. I've never used Logic Sheet, but it gets better ratings than XLMiner Analysis Toolpak. So maybe I'll try it sometime over Christmas break or something, see how it goes. But this is what I'm used to, so I'm saying go ahead and load this, and you need to do this for Thursday's assignment. Load it, install it, and once you got it installed, then you can use it. How? Go back to your add-ons menu. You should see it there. Go to it, choose Start. Brings up an extra window here. It can do a lot of different things. Lots of different things there. The one we want is the linear regression right there. You need to fill in these boxes to get some output, is the point. That output is going to include the regression line, its equation. But it's going to include a lot more than that. It's going to include a lot of other output that is useful for more than just getting the observed regression line for this sample, say, this random sample. Yeah. From a bigger population. It's going to also allow us to do inference. What does inference mean? Talked about that. You should be able to define inference on the final exam. I'm not going to ask you to do so, but theoretically you should be able to. What is inference? Infer, somewhat synonymous with predict. What does it mean? Statistical inference in the broad, big scheme of things. I'm doing something to try to give you another hint. Yeah, you could kind of say extrapolation. Go from a sample to make predictions about population. That's inference. How do we do it? So far, it's been with confidence intervals and hypothesis testing. Here in chapter 11, we're actually adding a third thing. You could call it model building. Coming up with equations to make predictions based on assumptions, models, in this case, a linear model. You don't have to just keep it to linear models. You could also do quadratic models and cubic models and trigonometric models and so forth. That you can generalize this stuff a lot. And we do that to some degree in applied stats in the spring. Model building, but within the model building, we still want to do the usual stuff. We still want to do confidence intervals and hypothesis testing. We also want to do another kind of interval called a prediction interval. Prediction intervals are confidence intervals, but we call them prediction intervals instead. We're still going to assign a level of confidence to them, like 95%, for example, but they're used for something a little different than the typical application, which is why we give them a different name and we call them prediction intervals. Let's get into the details. First thing to do, I always do, as a default, is click the labels box. I want to write this down. And when you're in the linear regression in XLMiner analysis Toolpak, first thing to do, click the labels box, although before you do so, you should really make sure your data points have labels for X and Y. At a bare minimum, they should be called X and Y. But ideally, you also say what they mean. This is problem 29 in the book. It's related to carbon dioxide emissions. X is the year, since year 0, whenever that is, and Y is CO2 emission. I don't know if it's for some power plant or something, some business. Yeah, coal-fired burners. Oh, way back in time, starting before I was born in 1965 and going through 1977, which, by the way, 1977, January 1977, it was the last year that the Vikings were in the Super Bowl. And I was not quite 9 years old yet. Of course, you know, they lost all 4 Super Bowls they were in back then. But I never imagined they'd never be in another Super Bowl since then, at the time. And never even be in another Super Bowl. Anyway, that's what makes me think of, one thing I think of when I think of 1977. I also think of a Twins baseball player named Rod Carew, who had an amazing year in 1977. 388 batting average with over 600 at bats. That's astonishing. Anyway, Y range, highlight the Y values first, including the label. Then click this Y range box, and you'll see the cell range for the Y values, including the label, C1:C8. Of course, you could just type that as well. Next, I'm going to click the X range, B1 through B8, and click the box, and a B1:B8 will show up. Again, you could just type it as well. I think I accidentally just clicked this box. That was by default was not clicked. I don't click constant is 0 box. I'm not even sure what that does. Does it try to do a fit assuming B0 is 0? That's what my guess would be, but I don't want to do that. You know, B0 was very close to 0 for the other example, but in general, you don't want to assume the intercept is 0. Keep the confidence level typically at 95%, though you could change it. Next, down here, I click the residuals and residual plots boxes. Could click the other ones, but I usually don't bother. Then you want to pick an output range and click this box before you click OK. What does this mean? What does it mean to choose an output range? It means, so you're going to get some output. And you want to choose the cell in the spreadsheet that's going to be the upper left corner of the output. Don't pick B1 or B5 or C5 because you've already got stuff there. Perhaps a good one to pick would be, say, D10. That'll be the upper left corner of the output, D10. Now click OK and the magic happens. Ready? 1, 2, 3, go. Summary output. There it is in all its glory. Summary output, including some graphs as well, including residual output. And something that I have no idea why it does it this way. Maybe this is why XLMiner gets lower ratings, because it repeats itself. Let me move this plot. Both in Excel and the Google Sheets, it like redoes itself down here. Like, why is that stuff there twice? Why haven't they fixed it? Why are they putting that? It's the same information there twice. I just feel like cutting that out right now. Okay. I don't need it twice. All right. They've got the capability of fixing it. Why don't they fix it? It's been there for years. I've been teaching about XLMiner in Excel since 2004. That's when I first learned about it. And they've never fixed it. Maybe they just like having it there. I don't know. What is this telling you? Well, one thing it's telling you are the intercept and the slope of the regression line. Right there in the lower left. You see the intercept is labeled with the word intercept. Hey, I don't see the word slope in there anywhere. Well, the second number, the negative 49.6 repeating, is the slope. Maybe we should confirm that. Review some formulas and confirm it. Even though this doesn't have the slope there, it's got the word, it's got year X, it's got the label for the X values. Why wouldn't it just call it a slope? Or at least a rate of change? Well, there's a good reason for it, actually. In chapter 12, which we don't get to, but we do in applied stats, multiple regression. You thought simple linear regression was hard. Wait till we get to multiple regression. Chapter 12, you page through it, there's a bunch of vectors and matrices everywhere. You end up having, for certain kinds of models, more than one slope, more than one rate of change, because you have more than one independent variable. It's multivariable calculus again. And so, you know, if you had 5 other variables, you wouldn't want to call them necessarily slope 1, slope 2, slope 3, slope 4, and slope 5. It's better to just label them with the variable name. What does the variable mean? But this is a slope. It is a rate of change of the regression line in this case with respect to X. Let's confirm the answers here by doing what we did last Thursday as quick as we can. For the purpose partially of just reviewing some formulas that I showed you last Thursday. Let's put a row for the sums, a row for the means, standard deviations, correlation. And we're doing this slope, intercept. The formulas did involve summations. So I'll do equals SUM, B2 through B8. There's the sum of the X's, copy and paste that over. There's the sum of the Y's for the means. How many data points do I have here? I've got 1, 2, 3, 4, 5, 6, 7. I could divide these numbers by 7 to get the means. I could also just do equals average. $55 divided by 7 is almost 8. Copy and paste that over. Standard deviations equals STDEV. No P. Don't put a P. B2 through B8. Copy and paste. Correlation, we're again, remember, was equals correl, 2 R's, 1 L. Between the B2 colon B8 and C2 colon C8, put a comma. Correlation is negative this time. Very close to -1. You can see the answer there, about negative 0.993. Well, that's because the slope of the regression line is negative. It is a very strong linear trend. I haven't graphed it, but if you made a scatter plot or a scattergram, as our book calls it, you would see a very strong negative linear trend with a negative slope. What was the slope? Use the formulas in the book with the summations. Or use the shortcut formula that I showed you involving the correlation that's not in the book. So remember I said last Thursday, a shortcut formula for the slope, if you know the correlation, is the correlation times the ratio of the standard deviation of the y values divided by the standard deviation of the x values. The formula in the book for the slope is more complicated, doesn't use the correlation. It's n times the summation of the xi's times the yi's. I goes from 1 to n. By the way, I'm not going to bother typically writing I goes from 1 to n because that's always what we do in this chapter. So to save a little time and space, I won't bother doing it. It's understood. Minus the sum of the xi's times the sum of the yi's, and it's good to use parentheses here. All divided by n times the sum of the xi squareds minus the sum of the xi's quantity squared. There is even a third formula I showed you on Thursday involving the SS quantities, which I won't bother showing you right now. Anyway, once you've got the correlation and if you've got the standard deviations as well, this is the quickest formula. Let's use the quick one at the moment. So it's the correlation from cell B13 here times the standard deviation of the y's divided by the standard deviation of the x's. There you see it, negative 49.6 repeating if it's not too small in the back of the room there. And that's the same as the XLMiner output said the slope was, negative 49.6 repeating. Negative 49 2/3. How about the intercept? The intercept has a simpler formula. B0 is the mean of the y's, y bar, minus B1 times x bar. That can be derived using the normal equations. It also makes kind of some intuitive sense because what it ends up implying is that the point in the plane whose coordinates are x bar and y bar will always be on the regression line. Sort of the ultimate center of mass in both the x and y directions, that point, because of this formula, will always be on the regression line. So for the spreadsheet, coming back here, y bars in cell C11 minus the slope we just found in B15 times x bar in B11. And there you see it's going to be a 911 2/3, and I do believe that was the intercept that was in the summary output as well. Got it? Is it? 911 2/3, yep. Okay, so we confirm the answers. What is all this other stuff about? Let's start with the easiest part, which is actually the bottom. And the bottom right, in fact, the lower and upper 95% things here. If you had to guess what, say, these numbers represent, do you think you could guess? Thinking in terms of inference from a sample to a population, and the kinds of things we do in inference, and the labels lower 95% and upper 95%, do you have a guess as to what that represents? It is also on the slope line instead of the intercept line. It is a confidence interval. What do we use confidence intervals for? To always estimate something, some population parameter, mu or sigma squared or p, population proportion, or difference of two means, mu1 minus mu2, or a difference of two proportions, p1 minus p2. This confidence interval is in the line that's representing the slope. So what parameter might we be estimating there? Big hint, I just said the word in the last sentence I said, or maybe the previous sentence. Slope. But wait a minute. Isn't this the slope? It's a sample slope, not a population slope. This 49.6 repeating is an observed value of a sample slope based on a random sample. It's not necessarily equal to the population slope, but what do I mean population slope? And is it really a random sample? Okay. There are assumptions we're making in saying this. We are assuming these numbers do represent, at least partially, in their y values at least, a random sample from a larger population. In their y values. Now let's look at the context of this problem again. Very long chapter. End of chapter 11. Quite a number of pages. Here's the problem. Following data represent carbon dioxide emissions from coal-fired boilers over a period of years from 1965 to 1977. The year numbers is the X value starting in year 0, which I guess is 1965, through year 12, 1977. The Y value is the CO2 emission from coal-fired boilers. For each one of those years, well, they're not super clear on whether that represents the emissions from one plant, one boiler, or an average of a bunch of boilers. They don't really say. For the sake of simplicity, well, this is going to seem a little funny. Assume for each year, this is the emissions from one boiler. Maybe different boilers, maybe not the same, but just one boiler. For each one of those years, it's like a random sample of size 1 from a population of all the boilers over the whole country, of which there could be thousands of them, I don't know. Random sample of size 1, oh boy. This seems like it might not be completely valid, but hang with me here. You do, in the theory, in the beginning of chapter 11, if you've done the reading, you might remember there is some theoretical discussion about the X values being fixed. You, in a sense, choose the X values, and the corresponding Y values being from a random sample. For each given X, you've got a random sample in this case of one boiler, and the Y value is the CO2 emissions from that one boiler. It's a random sample from a larger population in the Y values. The Y value, X values are fixed and decided by you, and the corresponding Y values are really represented by random variables. Probability. They are random. They've got distributions, PDFs, CDFs, means, etc. This equation, which is in a form I did not write down last Thursday. I did not write down anything exactly like this last Thursday. I wrote down two other linear equations that were different than this, though similar. One thing I wrote down last Thursday was y hat equals b0 plus b1x, little b0 plus little b1x. Another equation I wrote down was mu y given x hat, this one doesn't have a hat, was b0 plus b1x. This is different. This is a mu without a hat. And instead of b's, we got betas. Greek letters. These are population parameters. Beta 0 and beta 1. Unknown fixed numbers that we'd like to estimate. Beta 1 is the population slope. That is what this confidence interval is trying to estimate with more than just a point estimate, more than just a negative 49.6 repeating, but an entire interval estimate. So we would write down a 95% confidence interval to estimate, maybe you want to write this down, I'm saying it verbally, a 95% confidence interval to estimate beta 1, emphasis on the beta and the 1. Beta 1 is what you see there, approximately negative 56.2 to negative 43.1. Say that again. Should probably be writing this down based on what we're seeing here. The answer for trusting this technology, a 95% confidence interval to estimate beta 1, beta sub 1 is about negative 56.2 to negative 43.1. Or in plus or minus notation, negative 49.6 repeating, or about negative 49.7, plus or minus some margin of error. The margin of error, mo, say for margin of error, can be computed by doing, for example, this number minus this number. I took negative 43.1 and subtracted negative 49.7. It's about 6.6. Negative 49.7 plus or minus 6.6 gives you a left endpoint of negative 56.2. Or I guess if we rounded it, it would be negative 56.1 if we rounded it using 6.6 as a margin of error. Better to keep more decimal places and only round at the end. So I'm sort of going against my own advice about that. And the right endpoint is this negative 43.1, negative 49.7 plus 6.6. I guess round to negative 43 point. Yeah, it would be negative 43.1. Okay. So you should be able to, based on this output, which you'll be using for problems 16 and 17 on the assignment due Thursday, you should be able to just state what the answer is, and you don't have to use any formulas. The answer is there for you, but you got to know where to find it. Let's go over here next to this t-stat. Negative 19.4. What is that? That is a t-statistic for a certain hypothesis test. And it's pretty far from 0. The p-value is very small. We're going to reject the null hypothesis, whatever that null hypothesis is. What is the null hypothesis in this context? I'll write it down and then we'll say the conclusion, then we'll take our stretch break. It's that the null is that the population slope beta 1 equals 0. For the p-value, it's always for the two-sided alternative that beta 1 is not equal to 0. Let's take our stretch break, then I'll write down the t-stat and we'll emphasize what it all means again. Get yourself psyched up again. Ready to finish off class. Not just today, but Thursday. You can do it. You can do it. A lot of details to keep track of in your mind in all of this. And when you read the book, on Moodle, I said, skim sections 11.2 and 11.3, because reading it in detail just makes you want to fall asleep. It's super duper complicated. Sections 11.2, especially at the beginning, most of the section 11.2, later in section 11.3, it gets more complicated. What is the t-stat? Here it is in general. This is on page 395, section 11.3, right there. It's a t-statistic. This has got the same kind of general form as all of our Z and T statistics in this kind of hypothesis testing context. It's an observed value of, well, either a mean like an X bar or a proportion like a P hat, or in this case, capital B1. I haven't seen capital B1 before. We've done little lowercase b1. Lowercase b1 is an observed sample slope. Capital B1 must be a statistic sample slope, right? Like the difference between lowercase x bar and capital X bar. That's a random variable. It's got a distribution. We'll say what the distribution is here in a minute or two. Subtract, what's this? Beta 1 superscript 0? What is that, beta 1 to the 0 power? No, it's not beta 1 to the 0 power, because if it was 0 power, that would be 1. That superscript there, that 0 is not a power. It's just telling you it's the null value of beta 1, which is 0 for the only test we do, and therefore, there's the simplified version of the test statistic. We always do this test in this class and also in applied stats. We don't test for beta 1 as something non-zero, though you could. So this is like a B1 minus 0, and then we're dividing by something, and that something has always been related really to standard deviations. Remember, for testing mu, we divided by, well, when we knew sigma, it was sigma over square root of n. When we didn't know sigma, we didn't know the population variance or standard deviation, we used s over square root of n. Later on, like in chapter 8, or was it 9, with proportions, it involves square roots of like p hat times 1 minus p hat over n. And like in chapter 10, it involved square roots that involve like the pooled variance and stuff. All those kind of formulas floating around in your mind a little bit. This is something somewhat similar. There's a square root there, if nothing else. S over square root of SSxx. I would write that one as SSxx, actually. That's what I would call that, based on what I told you last Thursday, SSxx. What's this S here? Is that a standard deviation? Well, not exactly. This gets confusing. It's called the regression standard error. In the spreadsheet output, it's observed values right there. Standard error 25.92296.279. That is the S in that formula we were just looking at. The observed value of S. What's that? That's what I called SSxx. What is that? I'll remind you. SSxx, I prefer using 2 S's to emphasize, in my mind, that it is a sum of squares. And it's this sum of squares. And that is a sum of squares. And yeah, I could write I goes from 1 to n, but I'm not going to bother. And where did I show this to you last Friday? I showed it to you when talking about the formula for B1. And I told you the way that I always remember it in terms of SS at first, and then I showed you how it was equivalent to the book's formula. And this does turn out to equal, though it takes a little work to verify this, the sum of the xi squareds minus the sum of the xi's quantity squared over n. That takes some verification. It's not super hard, but it does take a little work. It's not completely obvious that that's true. So what is this going to equal for this example? What I'd like to do is what I'm trying to get at is I'm trying to confirm the value of this t-stat, this negative 19.4. That's where I'm trying to get to. I'm trying to use the formula in the book right here. And right at the moment, I'm trying to say what SSxx is, which the book just writes as SSxx. I got to use this. So I'm going to need to, if I want to confirm all this, I need to add more to the spreadsheet like we did last Thursday. It's the abstract statistic representing whose observed value we've been calling lowercase b1. Capital B1 is a statistic. It's a random variable with a distribution from a random sample whose observed value is the little b1. So we need to add more to the spreadsheet here if we're going to confirm this stuff. Let's go ahead and compute x squared values. Excuse me. Xi times yi values. I'm not putting subscripts. I won't need y squared values for doing what we're doing here. You could compute y squared values for confirming the correlation, but that's beyond what we're doing. So here I need to square the x values. So I could do, for example, equals b2 squared here in cell D2. Copy and paste that down by clicking and dragging. And actually, I could copy and paste this entire column to the right into column E to get the corresponding y squared. No, I can't do that. That would be the y squared values, but I don't want that. Sorry. I would now in column E want the x times y values equals b2 times c2. We'll do that. I will share this Google Doc with you after class, but I hope you're really focusing on what I'm saying, at least. I need the summations of those things, right? So I can copy and paste this over. There's the summations. What is SSxx, for example? What's its value? I need to do that. I guess I need to make this smaller. Looking in up here at the same time I type, I need the sum of the x squareds. That's in cell D10 minus the sum of the x's quantity squared, this 55 needs to get squared, divided by n. N was 7 here, sample size. So it looks like the observed value of what I'm calling SSxx is going to be 102.857. There is actually another way to find this. Let me mention the other way. The other way to find that is to note that the formula for SSxx is actually related to the formula for the standard deviation of the x's. The sample standard deviation of the x's is the square root of the variance of the x's, and the variance of the x's is this summation, which looks really familiar, divided by n minus 1. The formula for the standard deviation involves SSxx. And therefore, if I know the standard deviation, I could solve this for SSxx, square both sides to get rid of the square root. SSxx can also be found by doing n minus 1 times the variance of the x's. Standard deviation of the x's is in cell B12. So if in cell G11 I type equals n minus 1, which is 6, times B12 squared, I do get the exact same answer. Yes, it worked. 102.857. But remember, what's the goal? The goal is to use that formula. I've got little b1, the observed value of capital B1. I've got SSxx. All I need is the S, the regression standard error. Well, it is in the the XLMiner output. It's this thing again. But it'd be nice to compute that some other way. Is there a formula for that regression standard error? Yes, there is. Yet another formula. It's, well, take the square root of both sides of this thing. Square root of SSE divided by n minus 2. Huh, n minus 2, really? Is that a typo? Should that be n minus 1? No, it's n minus 2. It's not a typo. Though, by the way, there are plenty of typos actually in this section. The sixth section is confusing enough as it is, but there are plenty of typos, especially on page 387. I'll just quickly say what they are. For example, right here, they say we're observing values of random variables that are called beta 1 and beta 2. No, they're not called beta 1 and beta 2. They're called capital B0 and capital B1. That's one typo. It's page 387. Another typo at the bottom of the page. That capital B1 should be a beta 1. Lots of weird little typos here and there. Not expecting you to remember that necessarily. Just realize when you read 11.2, the beginning of 11.2, there's some typos. And so if something doesn't make sense, maybe it's because it's a typo. Yeah, there's a formula for SSE, or a formula for S squared. This is, again, its square root is called the regression standard error. S squared is SSE divided by n minus 2. So S itself, the regression standard error, not standard deviation, but standard error, though it could be thought of as kind of a standard deviation, is square root of SSE divided by n minus 2. So we need to find SSE. We did that last Thursday with the other data set. Let's do it again today with this new data set. SSE, what do we need to do? Well, what was the formula for SSE? So many formulas. SSE, remember we did at the beginning of class today, was this summation. Initially written EI squared, ultimately written, well, you could write it like this. And then they distributed the minus sign through. Let me leave it like that. I need, for the data values, the yi's and the xi's, I also need the sample, slope, and intercept that we already found to compute the summation. These things are called residuals that I'm squaring. These things, same as the EI's. Has nothing to do with the number E. So I need the y coordinates of the data points. I also need the regression, intercept, and slope, and the x coordinates. In fact, you may want to do these values first. B0 plus B1 xi. Those are called yi hats. They're predicted y's. Predicted y's. Yi hat. I could call them y hat if I wanted to for short. Why? I don't like my mouse pad. Click where it should work and it doesn't work. What in the world? Where are the slope and intercept? The slope is in cell B15, the intercept's in cell B16. Okay, B15 is the slope. Go B16, $B, $16 for the intercept, plus $B, $15 for the slope, times B2 for X. I need the dollar signs because of I need the intercept and slope to be the fixed cell references. B2 doesn't have dollar signs because I want that to change as I copy and paste down to B3, then B4, then B5. These numbers should be close to the y values. Yeah, compare column C and column F, they're pretty close together. Not as close as the other example, but relatively close. The residuals now are the y values in column C minus the corresponding y hat value in column F. Residuals average out to 0. In fact, if you sum the residuals, you get up to rounding 0. But if you square them, squared residuals, of course, they're not going to be negative. You'll get a bunch of positive numbers. And okay, let's relabel this thing here. And SSE is now the sum of those squared errors, residuals. I can just copy and paste the summation formula to column H. That's SSE 3360. S is sum of squares. E stands for errors, which is synonymous with residuals. To get the regression standard error, I'll put that down here. We need to take square root of SSE divided by n minus 2, which is 5. 25.9229. Breath, we're almost done here. 25.9229. That is the observed value for this sample of the regression standard error. What does it estimate? Haven't said that yet. 25.9229. Hey, yeah, there it is. 25.9229. 6279. It's in the it's in the output. Last thing to do here is confirm again this formula. It's not the very last thing to do today, but last thing to do for what we're trying to do, we've been trying to do for the past 20 minutes, is we're trying to verify this formula and the t-stat in the output B1, I'll just call it T-stat here. The formula was B1, cell B15, divided by the ratio of S, regression standard error, divided by square root of SSxx. That number should look familiar, negative 19.4. Yeah, it was in the table at the bottom. That's what we've been doing the past 20 minutes, is trying to confirm that. Negative 19.4. Yes, it's right there. And that's a pretty extreme t-stat, pretty far from zero. The p-value is very small. Therefore, with how many degrees of freedom? N minus 2 degrees of freedom. Yes, that's right, n minus 2. We reject this null hypothesis in favor of the alternative. We say the population slope is non-zero. If we wanted a p-value for a one-tailed test, say a left-tailed test, because it seems like the slope is negative, though we really should decide on the kind of test before you gather the data. As the years go by, the emissions go down. That makes intuitive sense because they've been implementing measures to improve the emissions. You should do a left-tailed test. You'd want to take the two-tailed p-value and divide by 2, making it even smaller. Definitely rejecting the null in that case. Some people always do a two-tailed test as a default, and that's what the XLMiner output is doing as a default. Two-tailed p-value, which would double any one-tailed p-value, making it harder to reject the null hypothesis, making it harder to make a type 1 error. Yeah, we're definitely rejecting the null. And what does that mean? That means everything we're doing is more worthwhile. Because if beta 1 were 0, why would we be doing regression in the first place? Beta 1 being 0 would mean that the value of x doesn't really affect y. If the slope is 0, the regression line would be horizontal. And that's saying x doesn't really affect y. So all this is to justify that using regression line is a good idea. This standard error here, 2.556, that represents the thing we divided by in computing the t-stat. The s over square root of SSxx will turn out to equal this 2.556. And that also can be confirmed by doing B1 divided by that equals this. If I do cell E30 divided by F30, E30 divided by F30, I get the t-stat negative 19.4. This number divided by this number gives you this number. And the p-value can be found with technology. You could also use your calculator to confirm the p-value based on n minus 2 degrees of freedom, which would be 5 in this case, 5 degrees of freedom. In 1 minute, what's all this based on? Various things. It's all based on, to start with, something called the regression model. Essentially this stuff on page 380, which I don't have time to get into right now. It's also based on all the nasty, messy derivations in section 11.2, crazy calculations, which, for example, ultimately derive this fact here. Capital B1 is a statistic. It's a random variable obtained from a random sample. And based on the assumptions of the regression model, it happens to be normal with this mean and this variance. Where sigma squared comes from the regression model, its square root is what the regression standard error approximates. The capital S. So what do you need to know? Well, for the homework and probably on the exam, You don't need to know all the derivations. You just need to know how it's used and how to read the output and that kind of stuff. And the formulas, put on your note card, but probably for the final exam, instead of just a note card, I'll let you use a whole piece of paper. Because there's just lots of formulas. And you don't have to write every single formula you find in this chapter, for sure. We want to highlight the most important ones, which are those that I talked about today. I've been putting the videos, the classes on YouTube. I'll put this one up too, in case you want to rewatch part of it, re-listen to something that I said. I'll try to put some timestamps up to help you find things as well. Okay? Have a good day.